Hello everyone. In today's lecture we are going to discuss a simple issue of constructing the model for the mass spring damper system. This is the most common engineering model, so it's mass spring damper system or model. Damper or viscous force can be captured with this feature. Okay, fine. So what do we have here? What do we have here is, let us think that here is just a block of the material placed at the surface, and we are taking the rope and we are dragging this block from the initial condition, which is t0, velocity 0, and position essentially 0, that we can place it here at 0 position. This is the x, and this block has a mass m. How do we model this? We already kind of anticipate modeling features. Precisely, we can say that there is a viscous or frictional force that is here reflected in this element that is damper. In addition to this, we have elastic force that is also present, elastic, and we know that this is k of x, while the friction force or damping force is a bx dot. This is the mass here, and this mass has been under the influence of this f of t. So this is schematic of the model. And if we write Newton's second law, we will obtain the following, that mx, which is double dot, which is inertial force, plus bx dot, which is damper or viscous force, plus elastic force, is balanced by this f of t, this force that is applied on this object. So we have a model. This is our model. And we are just interested in finding out model here, and we are just interested in finding out what is the state space representation of this model. In other words, state space, because this is mechanical system, this is heritage of the mechanics, and we know that the state space essentially represents the space of all possible positions of the rigid object, and this is given as follows. We say that x, which is x of t position, is just some state variable z1. I'm calling this as a z1 of t. Therefore, this leads me to the following notion that if this is position, that derivative of the position is velocity. So I'm having that dx by dt is the same by claiming that dz1 by dt is equal z2, and this is velocity. In other words, I want to represent this model in the world of the velocities and positions. If we take this, we also recognize that the second derivative of the position is acceleration, but the first derivative of the velocity is acceleration. In other words, we can write that this is m z2 dot plus b x dot, but x dot is again z2. Here we see bx dot plus k z1, and this is equal f of t. We already generated some first derivatives here, and here we have obviously one OD, and here is a second OD. Therefore, we can write as follows the system of the ODs. So we can write z1 z2 dot dot equal, and I will write in the matrix form. I divide this entire equation by m, and therefore this becomes 0, 1 minus, here it's k, m, here is minus b by m, z1, z2, okay, plus 0, 1 by m f of t. Okay. In other words, we obtain the state space, we obtain the structure z dot equal a of x plus bu, where now this is matrix A and this is matrix B. Okay. So this is obtained state space. Now we usually have a system that is given as A, B, C, and D. What are in this case C and D? And in this case, if, let's say, position is desired output, we have that y of t is equal 1, 0, z1, z2 plus 0 f of t, f of t. In other words, we obtained that C is this matrix and D is the following matrix. Therefore, we have a state space realization A, B, C, and D. And now let us look into the last important thing. How do we realize this in reality? So realization. So when we say realization, we refer to the three elements. One is an integrator, gain, and summation or subtraction element. Okay. In other words, we want to use just these three elements, integrator, gain, simple gain, or amplifier, and summation element. Okay, and let us now look into the equations. How do we realize this? Okay, so keep in mind that this is A, B, C, and D, and let us write that U starts here as input, which is f of t, multiplies the block 1 by m, it's a gain. Okay. Goes into the summation element because I want f of t plus 1 by m plus I want to generate all of this. Okay, so it comes here and it generates the following. So I'm claiming, since I have a two states, Z1 and Z2, Z2, that Z2 has to have integrator, because I have to integrate these states Z2 to get the Z2. Therefore, I'm integrating Z2 and I'm obtaining the signal Z2. I'm multiplying this signal Z2 with minus B divided by N, and I'm adding. Okay, so Z2 multiplies this. Now, I see that this Z2, it's nothing but Z1 dot. So there is another integrator here, because this is Z1 dot from the equation. We integrate the Z1 dot, we get the Z1 signal. Okay. And now we just need here minus K by M signal to add here to generate Z dot 2, because Z dot 2 is this term multiplies Z1, which is Z1 multiplies this, adds to it. It's here Z2 minus Bn, it's added here, and this is how our realization looks like. Finally, we have that this is just multiplied by C matrix, or just by 1, and we get Y of t. Okay, this is the pretty much realization. Interestingly enough, we will show that this realization, just these simple elements, leads to the transfer function that is given by this green box. So this is the transfer function, or input-output. This is the inheritance of electrical engineering. In other words, if we realize the modeling of this system by these electrical engineering elements, which this is just a summation, simple gain, and integration, we can design the relationship between a force and the position in this mechanical system. Therefore, we conceptually presented state space modeling from the first principle equations mechanics, and when we do the realization with the integrator gain and summation, we obtain something that is input-output or transfer function system representation.